Lesson: Evaluating and tuning machine learning models. Evaluating and tuning machine learning models is a critical aspect of developing robust AI-driven solutions, especially in sectors such as supply chain management, where decisions can have significant operational impacts. Understanding how to assess and refine models ensures they perform accurately and efficiently in real-world scenarios. This lesson explores practical tools, frameworks, and methodologies that professionals can implement to enhance their proficiency in evaluating and tuning machine learning models. The journey begins with model evaluation, a process that involves determining how well a model performs on unseen data. This is crucial because a model might perform exceptionally well on training data, but poorly on new data, a phenomenon known as overfitting. To assess model performance, practitioners use various metrics depending on the type of problem classification or regression. For classification problems, common metrics include accuracy, precision, recall, F1 score, and area under the ROC curve. For regression tasks, metrics such as mean absolute error, mean squared error, and R-squared are frequently utilized. For instance, consider a supply chain scenario where a machine learning model is used to classify products as either high demand or low demand. In this context, precision and recall are particularly important. High precision indicates that when the model predicts a product as high demand, it is often correct, which is crucial for inventory management. High recall, on the other hand, ensures that most high-demand products are identified, minimizing stockouts. By balancing these metrics using the F1 score, supply chain analysts can ensure that the model provides reliable predictions for inventory decisions. Cross-validation is a robust method for evaluating model performance. It involves partitioning the dataset into multiple subsets, training the model on some subsets while validating it on others, and repeating this process multiple times. This technique provides a more accurate estimate of model performance by mitigating the variance that might arise from a single train test split. In practice, k-fold cross-validation is commonly used, where the data is divided into k subsets and the model is trained and tested k times, each time using a different fold as the test set. After evaluating the model, the next step is tuning, which involves adjusting the model's parameters to improve performance. This process is often referred to as hyperparameter tuning. Unlike model parameters, which are learned from the data during training, hyperparameters are set prior to the learning process and control the overall behavior of the model. Common hyperparameters include learning rate, number of layers in a neural network, and the complexity of decision trees. Grid search and random search are two popular methods for hyperparameter tuning. Grid search systematically explores a specified subset of the hyperparameter space, evaluating all possible combinations. Although comprehensive, this approach can be computationally expensive, especially with large parameter grids. Random search, on the other hand, randomly samples from the hyperparameter space and often finds good results with fewer iterations. In supply chain applications, where computational resources may be constrained, random search offers a practical balance between thoroughness and efficiency. Another advanced approach to hyperparameter tuning is Bayesian optimization, which models the performance of the hyperparameters as a probabilistic function and iteratively updates this model to explore promising regions of the hyperparameter space. This method is particularly useful for complex models with many hyperparameters, as it often converges to optimal configurations more quickly than grid or random search. Consider a case study in which a supply chain company aims to optimize its machine learning model for demand forecasting. By employing Bayesian optimization, the company can efficiently explore the hyperparameter space of its gradient boosting model, ultimately improving forecast accuracy and reducing inventory costs. This real-world example illustrates how advanced tuning techniques can directly impact operational efficiency and cost-effectiveness. The importance of model evaluation and tuning is further underscored by the concept of model interpretability. In supply chain contexts, understanding why a model makes certain predictions is as important as the predictions themselves. Techniques such as SHAP provide insights into feature importance, helping analysts understand the model's decision-making process. By interpreting model outputs, supply chain professionals can make informed decisions, justify model predictions to stakeholders, and identify potential areas for improvement. In addition to these methodologies, practical tools and frameworks facilitate the evaluation and tuning process. Scikit-learn, a popular Python library, offers a wealth of utilities for model evaluation and hyperparameter tuning, including functions for cross-validation, grid search, and random search. TensorFlow and PyTorch, two leading deep learning frameworks, also provide capabilities for tuning complex neural networks. These tools are essential for supply chain analysts seeking to leverage machine learning in their operations. To illustrate the application of these tools, consider a scenario where a supply chain analyst uses scikit-learn to improve a model for predicting supplier lead times. By implementing cross-validation and random search, the analyst can systematically evaluate and tune the model, ultimately achieving more reliable predictions that enhance supply chain resilience. In conclusion, evaluating and tuning machine learning models is a critical process that ensures the development of reliable, efficient, and interpretable models, particularly in the supply chain domain. By leveraging metrics, cross-validation, hyperparameter tuning techniques, and practical tools and frameworks, professionals can enhance their proficiency in building robust AI-driven solutions. As supply chains become increasingly complex, the ability to fine-tune machine learning models will be an invaluable skill, driving operational excellence and competitive advantage in the industry.